Cycle 2, Lesson 8. In the next few lessons, we're going to look at combining functions, by which we mean adding, subtracting, multiplying, dividing, or even putting one function into another. That's actually called composite functions. For this particular one, we're going to look at adding and subtracting in particular, though. So, the superposition principle. That states that the sum of two or more functions can be found by adding the ordinates, which are the y values, while at each abscissa. So in other words, we want to add the y coordinates. We're going to add the y coordinates together while keeping the x coordinates the same. So if I want to add the point, say, 2, 3 and 2, 4, notice how 2, 3 and 2, 4 both have the same x coordinate. I would add the 3 and the 4 together and I'd get a new point, 2, 7. Very simple, and if you're still wrapping your head around it, then of course there'll be some examples to help you with that. But that's the idea. Add the y coordinates, keep x coordinates the same. So, student council is selling t-shirts to raise money for new volleyball equipment. There is a fixed cost of $200 for producing t-shirts, plus a variable cost of $5 per t-shirt. Councils decided to sell the t-shirts for $8 each. Write the equations to represent the cost and the revenue as a function of n. So, the cost is going to be $5 per shirt, but there's also that $200 setup fee, right? So that's maybe to design it or whatever. That's the cost function. Here's the revenue function. They're going to get $8 for every t-shirt they sell. So just rough sketch. Here's what the revenue function will look something like. That's R at n. And the cost function is going to look something like this. It's going to start a little higher but not be as steep. And clearly they cross each other because they have different slopes. Let's do it in Desmos, though. I mean, there's a sketch, but let's actually do it in Desmos. Again, I'm switching C and N for Y and X, but that doesn't matter. 5x plus 200. And Y equals 8x. These don't fit nicely on our grid, of course. The numbers are too big. Let us just play with the x-axis a little. Let's go negative 10, so I can keep the x-axis in there, up to 20. See what happens. No. I guess that's a bit better. But I haven't gone far enough. Okay, let's change this 20, or it's 30 now, to 100. Okay, now we can see better what's going on. So we can play with Desmos a bit to make things fit. We can see the point of intersection is 6.6 repeating. So what does that tell us? Well, 66.7 or 67 t-shirts approximately is going to be where they break even. So the break-even point was 66.7, and I think it was 533.3. So that tells us when approximately 67 shirts are sold, then we break even. In other words, the cost of, we'll have spent $533 on costs for the t-shirts from making the t-shirts, but we'll also have got $533 back in sales if we sell that number. So we'll be back to not having any made any money or lost any money. But every t-shirt we sell after that is going to gain us a bit of money. Develop an algebraic and graphical model for the profit function, which is R at n minus C at n. So if I want R at n, sorry, P at n for profit, is going to be 8x, that was our revenue function. Remember, I'm just taking them from up above, and it's not x, it's n, minus 5n plus 200. I'm putting that in brackets to keep my signs correct. And then if I take the brackets off, then I can end up simplifying it. I'll end up with 3n minus 200. And if I graph that, y equals 3x minus 200. You can see we've got this third line here, which is a combination of these two things, and it has its x-intercept, its break-even point, at exactly the same place as the point of intersection was for the other two graphs. This might seem really familiar. We've done this kind of thing when we're solving equations using method 1, which sort of corresponds to looking at the two lines point of intersection, and method 2, where we put two things together, just like we did here, and find where they cross the x-intercept. So we've already been combining functions, it turns out. Actually, we haven't been combining them. We've been taking them apart. They've been starting as one function, and we've been breaking them apart. But we've been working with it. So, something like this, and again, we have our point of intersection of 66. Is the x value. So what do we do? How does this work? All right, so let's imagine we've got two functions. We've got a function f, which has the points negative 4, 4, and so on. We've got another function g, and it should say f at x, g at x. I mean, normally that's how we do it. But anyway, so they're f and g, they're two separate functions. If we want to add these together, then we can get a combined function, again, by looking for where the x-coordinates are the same. So here's 2 points, one in each function, that have the same x-coordinate of negative 4. I'm going to use the squiggle bracket to show it's a set, then this round bracket for this particular point. Remember, we keep the x-coordinate the same, but if we're going to add them, then we add the y-coordinates. 4 plus 2 equals 6. So we get this new combined point of negative 4, 6. Then I look for a next place where I got a y value, the x value is the same. There is no negative 2 in this function here, so let's not worry about that then. Let's move on to the next one. 1, 1, yeah, we do have that one. So you notice how I skipped right over the negative 2. I skipped right over this point, and I skipped over this point because there's no x-coordinates that match up in the other function with them. So we can't add together points unless we got one in each function. So I'm only adding the ones where they have x's that line up. So the x stays the same, I got 1, 5. And then I look for the next place where I got matching x's. And I see that that doesn't happen until I get to 4, 6, and 4, 4. Again, skipping over 3, 5, and 2, 2. And when I do that, I keep the x the same, I add the y's, and I've got 4, 10. So I added them together. You can probably imagine that subtracting, or you can imagine how subtracting is going to go. In fact, I'm just going to circle the points I want to use. These are the only ones where the x's combine, so we can ignore those ones that I'm not circling. In A part, I added them. In B part, I'm going to subtract the y's, again keeping the x's the same. So I'm taking away g from f. So I'm going to take away the y-coordinate in the point in g from the y-coordinate in f. So I'm going to do 4 minus 2. and I'm going to keep my 1 the same. I'm going to do 3 minus 2. And I'm going to keep my 4x the same, and I'm going to do 6 minus 4. And then that's all I can do. Now notice C part is also subtract, but now we're switching it around. Now we're doing G, we're taking F away from G, so that changes the order of the subtraction. Still keeping the x's the same, but now I'm going to do this one, 2 minus the 4 in this one, so the order is changed. 2 minus 4 is negative 2. I've got a 1, I've got 2 minus 3, which is negative 1. And I've got a 4, and I've got 4 minus 6, which is negative 2. Notice how, when I just switched the order of the subtraction around, I ended up with the same y values, but the signs were just opposite. Use the graph of f and x to sketch the graph of f and g, f plus g, and f minus g. All right, so I need to get some key points here. So the key points, I'm going to write that down. Identify key points, because that's really the easiest way to do it. Just like in doing transformations, when we want to know what some key points are and then transform them, we want to do the same thing. We want to identify key points for combining functions. So I see I've got the point 0, 3. And just looking along the line here, I can see I got another one at 4, 6. And another one at 8, 9. And at 4, 0. And at, negative 4, 0, negative 8, negative 3. Okay, so those are some points that I won't write them all down, but we can clearly read them. If I do the same thing on G, I got again the point negative 4, 0, but I've also got the point negative 8, 1, I've got 0, negative 1, 4, negative 2, and 8, negative 3. So I can do the same thing as I've done up here, up above. It's just that instead of being given points, I'm picking my own points, and then I'm going to either add or subtract them. So if I want to add them, let's do this in green. So I'm going to look where the x coordinates line up, say these two, where x is negative 8, and I'm going to add those two y coordinates together. So I'm going to add 1 and negative 3. 1 plus negative 3 gives me negative 2. That's my new y coordinate, keeping the x coordinate the same. At negative 4, I've got y coordinates of 0. 0 plus 0 is still 0. And then here, I'm going to add negative 1 and 3, and I'm going to get positive 2. I'm going to add negative 2 and 6 and get positive 4. I'm going to add negative 2 and positive 9 and get positive 7. 7? 9? Oh, it's negative 3. So positive 6. And you can see that if I add two straight lines together, I still get a straight line. So this is the graph of f plus g. Now if I want to do f minus g, then I'm going to subtract the y-coordinates on the red line from the y-coordinates on the blue line. So it always gets a bit trickier with the subtracting. So I'm going to start with this one, negative 8. So the blue line, the y-coordinate of negative 3, is what I'm starting with, and I'm subtracting the y-coordinate from the red line, and I'm actually going to get negative 4 out of that. So I'm actually going to get a y-coordinate, which is below, while keeping the x-coordinates together. Again, I'm still going to have 0 because 0 minus 0, no matter how you do it, is going to still be 0. Then I've got the 3 minus negative 1 for this one. Again, we've got a double negative going on here. Now we end up with a positive 4. For this one, we've got 6 minus negative 2. That's going to give me positive 8. And then for the last one, I've got 9 minus negative 3, that's going to give me positive 12, which is off the graph, but it's going to be up there somewhere. Here's the sketch. And that's f minus g. So we can do it with graphs. Last example, skier is skiing downhill. It's 100 meters long at a constant speed of 1 meter per second. He goes, or she goes through a series of moguls, which are small hills. The constant slope of the hill is negative 1 meters. Assuming that the moguls measure 1.5 meters from crest to trough and are roughly 5 meters apart, develop an algebraic and graphical model of the height of the skier versus time. Okay, so there's two things going on. One of them's pretty easy. That's the 100-meter hill and going down traveling at 1 meter per second, right? So if we think about the height of the skier just going down the hill, excluding the moguls, then we could call it, well, let's call this h at t, and we would get 100 meters, and then they go down 1 meter per second, so minus 1 meter per second. So it's linear, right? Let's graph that. Y equals 100 minus 1x, or just minus x. Obviously, again, that's not going to fit, so I'll just zoom out a bit, and there it is. So if there are no moguls, that would be a good representation of the skier's path. But there are moguls, so we have to take them into account as well. So to do that, let's picture the moguls as if they weren't on a hill. So let's imagine they're on flat ground now. What we've got is something that's kind of look like this. Right? Moguls go up and down, and that might look sort of familiar to us because we've just been talking about trig functions, and they're going to repeat. So from the information, they're 1.5 meters from crest to trough. So that means that the difference between the crest and the trough is 1.5 meters. Let's say it's plus 0.75 and minus 0.75. And we know that they're roughly 5 meters apart. Well, that just gives us our period. And we can come up with an equation. We just talked about trig functions recently. We can say that, let's say m for mogul is equal to the amplitude. Actually, before I even do the equation, let's identify the different parts. So I'm not just pulling out of nowhere. The amplitude is, I hope, clearly 0.75. If I use sine, then it starts exactly where I want it to. So d would be 0. There is no horizontal shift if I choose to use the sine function. Also, there is no c value. It hasn't been shifted up or down. I've set it right on the x-axis. However, I do have to figure out k. Remember, we do that by doing 2 pi minus the period. So k is 2 pi over 5. All right. So our function is going to be m equals 0.75 sine, and then k 2 pi over 5, and I'll use t. I guess I should have done m at t. So there is our function for that. Let's put that into Desmos. Maybe let's see how things go if we combine combine trig with linear. Y equals 0.75 sine 2 pi over 5 and Is this in radians? Just make sure it's all good to go. It's in radians. It looks very linear. Oh, and the reason it looks very linear is because I did not put my variable in there. That's better. It looks a lot less linear now. I was thinking it was just that I'd zoomed out too much. But no, you can see that it's clearly a sine function. It just looks very small because of how much I've zoomed out. All right, so how do we combine this into a ski hill? Well, the combine function, I'm going to just call this one S for ski, at t is going to equal the two things going on, so that the hill, the slope of the hill, plus the moguls over time would then give us 100 minus t plus 0.75 2 pi over 5 t. Let's graph it and see what magic happens. Let's hide these ones. Y equals 100 minus x plus 0.75 sine 2 pi divided by 5x. Wow, look at that. Looks just like a beautiful ski hill, complete with moguls. So we put the two together and we've got a function that represents an actual trip down a theoretical ski hill. So we start at 100 meters high, and since it's got a constant slope down, it's going to end up 100 meters out, and it's going to be a, well, I am a terrible artist, aren't I? It's going to go like this, kinda. Fantastic.